Well, hello everybody and welcome to our webinar today focused on phytoremediation. As you all know, I usually have a few housekeeping details to share before introducing our speaker, and then we'll get going with this presentation by Paul Thomas. This is a 60-minute session which has been approved for 1 professional development hour by APA and LACIS. You do need to stay for the duration to receive credit, and you will receive a certificate if you indicated that you needed LACIS, APA, CITES, CDT, LEED, or any other type of credit when you registered, of course, only if you're licensed and certified with those organizations. If you are a licensed landscape architect and you wish to receive LACIS credit, you must take a quiz, which will arrive as a SurveyMonkey link in a separate email from me following the session. If you're not licensed, you do not need to take that quiz. About evaluations, as an approved credit provider, we are required to offer a way for you to provide feedback. At the conclusion of the session, a survey link will appear in Zoom in the same window that you have open now. Ideally, you just complete it right away, but if you're racing on to the next meeting, you will also receive a Zoom follow-up email tomorrow that contains that same survey link. So you've got 2 options. As this is a webinar format, all attendees have entered in mute. However, when we shift to Q&A, I will be able to take each of you off of mute if you want to ask a question. So just use the Q&A button, and you can do this throughout the presentation. You don't need to wait until the end. So the Q&A button at the bottom of your Zoom window to pose your question. Also, there are a few additional resources that Paul has shared with us. I have added those to our wiki page for this event on our Design Workshop internal portal, and I will also be pasting them in the chat once we're underway. So the presentation will be about 40 minutes, and then the Q&A will take up the balance of our hour. So I'm now going to shift into introducing our speaker and extending a warm welcome to Paul Thomas and also Tara Gatliff, who has joined us today. So we're just really grateful for you to come and share your knowledge with us and talk about ways that we as landscape architects and planners can partner with you as well. Paul Thomas is a geologist with over 30 years of professional consulting experience and has conducted environmental characterization and remedial actions at major industrial facilities throughout the US. His work has resulted directly in the completion of full-scale design-build remediation projects in 25 states. He has also been involved in all aspects of due diligence, ecological characterization and mitigation, remediation, and regulatory compliance. In 1983, he began applying his knowledge of geology and computer methods to the management of hazardous waste through site characterization and remediation. Beginning in 1987, Thomas was among the pioneering practitioners of vegetation-based remediation and waste management, aka phytotechnology. Thomas founded Applied Natural Sciences with Edward Gatliff in 1994, developing the Treemediation program and implementing TreeWell technology at sites around the world. So as design professionals, we are always looking for cost-effective and sustainable ways to manage environmental toxins on some of our projects. And Paul, being one of the pioneers of phytoremediation techniques and the president of Applied Natural Science, is here with us today to share his 30+ years of experience on how phytoremediation can be applied in a wide range of environmental circumstances. So thank you so much, Paul and Tara, for being with us today. And Paul, you can take it away.
Thank you very much, Allison. And As I discussed earlier, I apologize in advance for any dog barking that might occur during the presentation. And with that, I'm just going to jump right into it here. Phytoremediation started as a technology that became generally accepted in the middle 90s. I got involved with it very, very early. And it became evident when I started into the technology that there were certain limits on phytoremediation as it was generally practiced. And one of the largest limitations was with regard to remediating groundwater. A lot of what I'm going to talk about today is pretty specific to groundwater remediation. Phytoremediation, of course, is also used for soil remediation. And when we talk about, in this presentation, when I talk about traditional phytoremediation, I'm talking about the use of vegetation to remediate contamination in what are relatively shallow soils, or when we're talking about groundwater, relatively shallow groundwater conditions. And by shallow, I mean in the upper 5 to 10 feet of the soil column. Specifically to what applied natural sciences does and has done, I'm going to also discuss briefly revegetation of impacted soils and soil vapor management. As I mentioned, the primary applications for phytoremediation are contaminant degradation and mass removal in soil and groundwater. In groundwater applications, it can also be used as a means of controlling hydrology so that you can direct plumes, contaminant plumes, from migrating where you don't want them to migrate. I'm not going to go into a great deal of detail regarding the processes of phytoremediation. For one thing, it's pretty well understood how plants have the potential to affect contaminants in shallow soils and groundwater. And the main remediation method that we use is increased degradation of contaminants by plants operating in conjunction with soil microbes. Now, this is generally a process applied to organic chemicals and not to contaminants like metals or other inorganic chemicals. What's happened over the years is that most applications of phytoremediation, particularly as we practice it at Applied Natural Sciences, is with regard to organic chemical degradation and remediation. And from that aspect, most of the treatment happens in the soil before the contaminants ever get to the plant, because most of what we're trying to accomplish is accomplished by either soil microbes or by degradation in the soil before the contamination gets to the plant. There are instances, however, with particular contaminants and under particular conditions where the plant does take an active role in either taking up and sequestering contaminants or transpiring them into the atmosphere. So I just touched on this a bit, but the primary target contaminants for phytoremediation are organic compounds, and this would include volatile organics, which could be anything from petroleum to solvents to organic pesticides. There are semi-volatile organic compounds that are more tar-like substances that are good targets for phytoremediation, particularly if they're in relatively shallow soil. Agricultural inorganic compounds is just a mouthful that generally applies to fertilizer. Phytoremediation can be an ideal way of dealing with excess nutrients in shallow groundwater or in soil for that matter. Metals contamination was a primary target of phytoremediation in early research. And it is still, phytoremediation is still used to remediate metals, but it has to happen under very particular circumstances for it to be superior to other technologies that are sometimes less expensive and easier to implement. The perfluoroalkyl substances here I throw in just because it's like the latest, greatest kind of sexy contaminant out there that everybody's talking about. And it's also a potential big target for phytoremediation. One of the things that makes it an attractive target for phytoremediation is that it's difficult to treat and that it doesn't degrade well in the soil or in the groundwater. It tends to be very recalcitrant, and these more stable compounds sometimes can be attacked with phytoremediation technologies better than with traditional remediation methods. So again, I'm using the term traditional phytoremediation here because that is a distinction between what was done in the past and what's still being done by a lot of practitioners, and what we did in moving away from those traditional approaches, primarily because of limitations on how deep we could go after groundwater and what kind of contaminant concentrations we could go after. So these limitations are what forced us to develop the technology that we have developed. And the things that we overcame were the inability to impact deep groundwater by confounding effects of percolating precipitation. Basically, I'm talking to an audience here that is a little unusual in that you understand more about how trees work in the environment. To a large extent, I'm normally talking to people whose expertise is more related to the chemistry of the contaminants that we're dealing with. So the trees are going to get their water from the easiest place that they can. And if they can survive on percolating precipitation, which is the case in most environments in the continental US anyway, where we work, the trees are not going to go after deeper water if they don't have to. And the other thing that we were trying to overcome is phytotoxicity resulting from higher concentrations of contaminants. So our approach is to be able to target specific depths in the soil column and in order to address contamination at specific depths in either soil or groundwater or soil gases. Our goal is to use trees primarily as pumps in order to move contaminated water upward through a constructed column of backfill soil. And we do this with an understanding of where the contamination is on sites, what are the zones where groundwater is moving, and how do we need to combine our remediation methods with what's been done in the past or what's going to be done concurrently or in the future. So we want to exclude surface water from percolating down and being available to this tree that we're using as a pump. We want to be able to get access to groundwater at least to the range of over 100 feet. And we want to get access to specific lithologic units, even as far as going into fractured bedrock. What our system does is allow us to address what would normally be phytotoxic levels of contamination by providing a large volume of potential contaminant reduction in a backfill soil column, which has the potential, based on measured concentrations, to reduce contaminant concentrations up to 90% before it ever gets to the tree. We also want to limit irrigation, because irrigation can be very counterproductive to our systems, in that long-term irrigation can make a tree dependent upon a shallow root system. And with a lot of our systems, if we have a static water level that's 20 feet deep, we need the tree to root as deeply as we can get it. And irrigation can make that difficult. So we want to have a system where irrigation is not necessary. So getting into some pictures here. We start off with a large diameter borehole that goes to our horizon of interest, whatever that may be, whether it's a layer in the fractured bedrock at 30 feet, or if it's a zone of glacial soil, at 15 to 20 feet. We start off by augering a large diameter hole down to this horizon of interest. And by large diameter, I mean from like 3 feet to 5 feet in diameter. Then we line that hole with a plastic liner that functions as a well casing, essentially. It forces the tree that's ultimately going to be planted in the top of this thing to get its water from wherever the bottom of that liner is, whether it's at 10 feet or 20 feet or 30 feet. Once the hole's completed, we have a steel platform that has this liner loaded onto it, that is placed over the hole by a skid steer with forks, and our goal being to keep people from going into the hole. That's our primary goal on all of these projects. So once that's placed over the hole, then the liner gets dropped. We place different types of tubing inside what we're calling a TreeWell unit, some for aeration, some for future fertilizer injections, some for taking samples of groundwater. And we also sometimes install clear PVC tubing that we can drop the camera down in to actually look at root development inside the TreeWell unit. So all of this is done through a grate at the surface that allows all of this work to go on without allowing people to fall into the hole. When we're done, a fairly typical installation will look something like this. We have a mound at the surface that we complete and plant a tree in, so that precipitation is shed off of this mound, and that plastic sleeve is brought up right around the trunk of the tree. So the tree is essentially sealed into this unit. Then we place a typical installation. We place a gravel mulch on the surface. We do this for several reasons, but there's certainly a lot of flexibility with how the surface completion goes, which is something that I'm sure would be of interest to anybody who wanted to incorporate something like this into a landscape design. We have a lot of flexibility in the types of trees we use. And also, as I was saying, with the surface completion, this is from a site in coastal Louisiana where we have to deal with storm surge. This particular site is near Lake Charles, and we had to deal with two direct hits last year. And the trees did surprisingly well. But the precast extensions at the surface are for that purpose, because we knew that we were going to be inundated periodically here. This is a site 3 years after planting, and I show it because it demonstrates a common issue we have with sites, in that a lot of our sites are industrial facilities that typically are maintained by people on riding mowers and spraying herbicides. And even if we tell people do not use herbicides on on our mounds. Sometimes they do. And in this case, we're going to have to go back and replant a lot of trees. But so this 3 years after planting should look a lot better than this. But this is a common issue we have, and even though our systems are not zero maintenance, there is a certain amount of maintenance required to keep everything operating. This is what we like to see down the road. This is a site in Pennsylvania 8 years after initial planting, and we have trees here that are using a lot of water, and we've had very good success here with actually cleaning up the contaminants that are in the ground. So the keys to our success are to thoroughly understand the site conditions. So this isn't really a black box system where somebody calls us and says, we need you to come in and install the system, and here's the area where we want you to work, and we come in and install it and leave. It's really not that kind of system. We have to work with the site owner and in most cases, the consultants that sometimes have spent years characterizing a site to be able to understand where the water's moving, where the contaminants are moving. And we also insist on doing our own pre-design investigation where we look at those types of things, but we also look at the water quality with an eye toward the agronomic considerations. We need to know if there are salinity issues or issues with elevated micronutrients that are normally not a concern for the people that are looking at these sites. So it's very important for us to be pretty intimately incorporated into the general knowledge of the site and the specific knowledge with respect to subsurface conditions. So just to kind of review how this TreeWell system works, the liner extends down to some portion of the total depth of that large diameter boring. In general, it's meant to, first of all, keep shallow percolating precipitation from being available to the tree roots. But it's also, on a lot of sites, meant to keep clean water that might be migrating laterally in that upper 10 to 20 feet from getting into this borehole and contributing to the water available to the tree. We want the tree to use the water that we want to be treated. When we do the backfill, we engineer the soil by controlling its texture and controlling its organic matter, and in some cases adding other types of treatment media to that backfill soil. Controlling the texture allows us to have control over how much capillary rise we get from the water table up into that soil column. Our goal being that the tree doesn't have to root down to, say, the water table's at 30 feet. We don't want the tree to have to root down to 30 feet. We want to have enough capillary rise so that that tree can get that water out and only have to root down, say, 15 to 20 feet. By adding increased organic matter to the backfill soil, we create a bioreactor effect that has the capacity to treat a large number of organic chemicals. In addition to the standard unit, which is the one on the left, which I just showed in the previous slide, we have another type of TreeWell unit, which I'm going to go to the next slide because you can see things a little bit better. We have a system that, instead of having an open bottom root sleeve liner, as was shown in the previous standard unit, we have a sealed bottom liner that, before the backfill soil is placed, we place a bentonite layer both outside and inside the bottom of that sealed liner, so that we have essentially a good seal in the bottom of the unit, and then we backfill with soil. Once that's done, before we plant the tree, we come in and install what is essentially a well inside the TreeWell unit that penetrates the bottom of that sealed liner. This allows us to target groundwater at depths significantly greater than we could normally do, because we are limited in how deep we can go with that large diameter boring. Once we get beyond 30 or 40 feet, it can become difficult to install that. So if we have groundwater that's at 100 or 150 feet, we need to have a well screen down where that contaminated water is. And we need to have that pass up into the TreeWell unit with a secondary screen that's inside the unit that allows water to come in the bottom screen and come out the top screen, providing water for the tree that's planted in the top to use. In order for this to work, there has to be enough hydraulic pressure on the water at that bottom screen that it rises up in that well casing to where it's inside the TreeWell unit. So this is only possible when we have that kind of condition, where we have a contaminated aquifer that's at some depth that has enough pressure that's going to allow the water to be up into that TreeWell unit. So basically, the TreeWell unit process is a large diameter hole that is backfilled with soil. The tree acts as a pump to move that contaminated water up through both the saturated soil column, that's part of that large diameter hole, where we can have anaerobic degradation processes, and the unsaturated portion of that hole, where we have more aerobic degradation processes. And there's the potential for what people think of with phytoremediation, where the contaminants actually get into the tree, or whatever the plant is that's being used, where it has the potential to be degraded or sequestered in the plant. This is certainly going to be the case with, for instance, we're currently working on addressing contaminant plumes down gradient from fly ash impoundments that are contaminated with what are relatively low levels of boron. And what we found is that a lot of these contaminant plumes are right in the sweet spot where the trees are going to take up virtually 100% of the boron that's in the groundwater, but it's not high enough of a concentration to kill the tree. So our goal is to have, and this is more like some of the original phytoremediation goals of treating metals. I mean, we're looking at actually mining this stuff out of the ground and then eventually harvesting the tree. And the other possibility is that contaminants are transpired into the air through the transpiration stream. And this is found to be the case with a lot of organic compounds. Got some examples here: 1,4-dioxane, MTBE, which is the old gasoline additive, and organochlorine pesticides. We had a site a while back where we were remediating lindane, and we found that a lot of the lindane was actually taken up into the tree and transpired into the air. And here we try to take advantage of what is often a relatively short half-life for some of these contaminants once they get into the air because of photodegradation processes. Whereas if they stay in the groundwater, they can be around for years and years. I'm going to touch really briefly on managing soil vapor, because this is something that we're still working through pilot projects and demonstration and data collection on. But we're pretty excited about the potential for this, because there's a large issue with the need to remediate and control soil gases that are contaminated by organic vapors coming off of contaminated groundwater. And these vapors have the potential to migrate, usually laterally, and into structures. What we have found is that it's possible to predict with some degree of accuracy the physical processes that result in these gases volatilizing from groundwater into soil vapors and back into groundwater, depending upon temperature and barometric pressure fluctuations. And what we have seen on sites is that TreeWell units have a capacity to act as a soil vapor sink, so to speak, in that changes in barometric pressure in a site actually pump soil vapors in the direction of least resistance. And if we have a penetration going down to where these soil vapors are volatilizing off of the water table, then we have a way for them to get out of the ground, and an alternative to them migrating into occupied structures. We've done other types of research over the years. This was a greenhouse study done to assess salinity tolerance of a number of different poplar and willow trees. Another area that we conducted a good deal of research on back in the late 90s and early 2000s was on quantifying transpiration rates. A lot of early phytoremediation practitioners relied on published rates for evapotranspiration that were a little bit difficult to hang your hat on, because they were often done under very specific climate conditions and with very specific plants. So what we did was actually directly measure sap flow, and I'm not going to get into the math here of how this was done, but the simplest way to explain how this works is that there is a heat source that either is wrapped around a plant stem or a heat source that goes right into the sap wood. And sap flow is a function of the heat transfer going up or down. And basically you can measure this in real time with sensors above and below that heat source that allows you to quantify sap flow. If it's a collar, then you can measure it directly. If it's a point source, then you have to measure the size of the trunk of the tree and then apply some calculations. But it's a pretty straightforward process. And what we did was measure both the sap flow and photosynthetically active solar radiation, which basically is the visible spectrum with a little bit extra on the ultraviolet and infrared end. And what we found was that you could draw a very good correlation between transpiration rates with the types of trees that we were using, specifically phreatophytic trees. But we've since done it on some other species and found pretty much the same thing. With other species, there are more variables introduced by relative humidity and wind and temperature. Willows and poplars we like to use because they're a little less coupled to the atmosphere and react pretty much in a straight line. If the sun's out, they're going to be transpiring water. And so what we found was that if we knew what the leaf area was above our sensor, we could come up with a unit evapotranspiration rate per unit of leaf area. And that's been very handy in us going forward and being able to predict how much water consumption we can expect from these trees. We also measured drawdown in response to daily evapotranspiration, and then looked at that from a hydraulic standpoint in order to calculate evapotranspiration based on drawdown. and they corroborated each other well. Same thing with lysimeter studies. The really tedious part of that particular research was coming up with real leaf areas. We didn't want to use leaf area index because that varies a lot from tree to tree, from one species to another. So we actually measured leaf area by counting leaves, and can be extremely tedious. I'm going to go through one case study here because it hits on a lot of issues that we have to deal with. This was a site in Sarasota, Florida. That L-shaped area that you see here was covered with mature trees, 80 feet tall. And at first glance, we thought, well, what are we going to do that hasn't already been done by those native trees? When we did the pre-design investigation, we found that those trees were getting virtually 100% of their water from that 0 to 7 feet of sand at the surface. And all of the contaminants were moving in the 7 to 15 feet of fractured bedrock that was beneath that sand. So we had a remaining source where the pump and treat was not working because that fractured bedrock didn't really lend itself to that type of system. And we had a 1,4-dioxane plume that was migrating off-site in that aquifer. So we basically took out the existing trees and put in over 150 TreeWell units using a range of different tree types. And what we found was that we had a pretty significant impact on groundwater flow direction. These yellow lines here are contours of the groundwater surface elevation before the trees had an impact. Once the trees started to transpire water, we found that they had the capacity to actually reverse the groundwater flow to the point where we were no longer getting off-site migration of the contaminants. And I'm not going to go into this in any detail because it's pretty simple. Basically, once we installed the trees, the concentrations went way, way down, in some cases to almost zero. And the result of that was that the pump and treat system was turned off. We had predicted that we would be able to clean the site up in 5 to 7 years. Actually, it happened in 4 years, and the state of Florida gave us a clean bill of health after 4 years of operation. Another site, and this is dealing with our revegetation experience. This was a spent bauxite site. An aluminum manufacturer would import bauxite into this harbor on the south side of the island of St. Croix. They would essentially extract the aluminum, and the result of that process was a liquid alumina that then was loaded back onto tankers and shipped back to the continental US for aluminum production. All of the waste material, the spent bauxite, the red mud, was left on the island. And the site that you see there in the foreground was about 100 feet thick. It had been there for going on to 50 years. Every time they had a storm, a hurricane or a tropical storm, a lot of that stuff was getting washed out into the ocean. And it was, in addition to being an eyesore, it was not good for the aquatic life. And so we were contracted because of our experience in doing revegetation of impacted soils, and by impacted I mean pH way out of whack, either high or low. High salinity because they used seawater to quench this process. So we set up, and this was just before they actually used our recommendations to revegetate the cover. We had a test plot right here. You can see a tiny green spot right in the middle. And this was kind of in the parent material part of the site. This is where the stuff was eroding. And we had a secondary test plot here, where we looked at a range of tropical grasses and a range of application of soil amendments that were available on the island. And about the only thing we had available to us was caliche, the coarse limestone, mostly shells, and organic matter that was from blow-down trees that would be chipped up and brought to the site. From a lot of stuff from Hurricane Hugo was still there and available to us. So that that was placed on the surface at rates and thicknesses that we recommended based on our test plots, and this is what it looked like a few months ago. So tremendous improvement. So we're looking at mainly the benefits of our system of phytoremediation that we call Phyto-Integrated Remediation, mainly because it's used in conjunction with other types of remediation. The positive aspects are that it is sustainable. We don't have any operation and maintenance costs that are resulting from power consumption or having to haul things to or from the site. It has the potential to be incorporated into landscape design in things like brownfield redevelopment sites and other types of potentially impacted sites. It's adaptable to a range of climates, and we've used it pretty much everywhere except for in the continental US, except for the desert Southwest and very low rainfall areas. There are still spots even in some mountainous areas where there's enough precipitation that this could work. And these are the sites that we've done to date. I think I left a few off of here, but you can see that they're kind of concentrated in kind of Rust Belt industrial areas. And we have quite a few sites in the western part of the country, and we're also working on a number of sites in Europe right now. So far, we're happy with the results. We'd like to do more, and hopefully we can work with you guys. So that's pretty much it for my part of the presentation. Do we have any questions?
Great.
Or
Paul, thank you so much. That was fascinating and full of detail. And yes, we do have two questions. So the first question, and by the way, we'll get started with these two, but I hope that others continue to put their questions into the Q&A. So the first question is from Josh Quigley. And Josh, I'm allowing you to talk, so you can now pose your question directly.
Sweet, thank you. I think you might have answered this a little bit after I asked it, but one thing I was curious about was, if biomagnification is an issue, if these plants or trees are removing these compounds, are they being concentrated in the plant material, and does that necessitate, removal of the plant material, or is that a worry that, there's potential for it to be reintroduced back into the soil, or, be moved off-site and concentrate as it moves up the food chain? So yeah, just curious if that's an issue or how to resolve that.
it certainly is an issue, and we've looked at it with a range of contaminants, and it's very contaminant specific, and it's also very, very plant specific. We found that with metals like zinc, for instance, when we've tried to get that out of the soil, one of the unexpected results is that most of the metals were sequestered in the root mass of the trees that we were using. In this case, it was poplar trees. And so the removal of that required us to actually extract the root mass, which we had not really thought that would be necessary. Other types of contaminants where accumulation has been a perceived issue has been where contaminants are transpired into the air. What we've generally seen is that contaminants that are taken up by the trees that we normally use and transpired, by the time the leaf litter starts to fall, the actual chemical compound that we're looking for is no longer detectable in the leaf matter. It is in the terminal branches in the fall, but by the following spring, it's not detectable anymore. It's really only a concern when we're dealing with contaminants that are sequestered and stay in the plant tissue. And those are going to be things like metals. And as I was describing with boron was a good example where we're actually looking at harvesting the trees after a period of, say, 10 years or so, and then starting with a new, with a new stand of trees.
Awesome. Thank you. Yeah, that makes a lot of sense. And I suppose it is significantly easier to remove it from plant material on the surface than 50 feet below. So that makes sense.
Yes. Yes.
Paul, we have another question from Betsy Peterson. Betsy, you can go ahead and ask your question with a specific example. Thanks.
Sure. Yeah, I think I have two questions now. One, I'm thinking of a site in Memphis, Tennessee, where there's a landfill in a public park. So I guess my first question is, do you work with landfills or is it more toxic waste sites?
We do work with landfills quite a bit.
Okay.
A lot of what landfills are requiring us to do is to reduce leachate seeps that are caused by the landfill, and we certainly have had success in doing that. But there is a concern with landfill leachate in that salinity is often an issue, and as you might imagine, that's something that if we're talking about using trees to consume this water as part of the process, then we've got to be very, very careful about what kind of levels we're talking about. So, but as far as other contaminants contained within landfill leachate, they kind of lend themselves to this type of process. But again, it's as long as we're within a proper range of salt, that we're okay.
Okay, that's helpful because this landfill is unlined and over a window to the city aquifer. So it seems like they need to do something with the leachate. I think my other question would be, are these sites typically fenced off and not accessible to the public, or would they be safe, let's say in this park, to do an installation and have people milling about on site?
We have a number of installations that are actually inside parks.
Okay.
And generally it's safe. The only time when it would not be is if we had an issue where there were contaminants that were at a high enough concentration inside the tree that it would be a possible exposure point. But by and large, with our system, the contamination is dealt with, particularly if we're talking about organic chemicals. Almost all of that remediation is occurring in the ground. It's not making it to the surface.
Okay. Thank you. That's very helpful.
Paul, we have a question from Luke. Luke, go ahead and ask your question.
Great. Thanks, Allison. Really quick one here, Paul. Given the spacing of the large diameter borings, it seems like there might be a significant amount of excavated material. I'm just curious how that gets treated or disposed of. Is that something on site, or does that have to be taken care of ex situ?
Well, that's a good question, and that actually varies depending upon the site conditions. We try to use as much of that material as possible in the construction of our mound that's at the surface, and that's usually possible because in most cases we have a certain amount of clean soil that we are drilling through before we get to impacted soil. And on most of our sites, we try to differentiate between clean versus dirty, and oftentimes we will stockpile the contaminated soil for testing and determination as to what's going to be done with it at a later date, essentially. And a lot of times that's done by screening with instrumentation at the surface. And on some sites, we just have to assume that 100% of the soil is contaminated until it's tested. And if that's the case, then it's stockpiled on site, and then it's either dealt with on site or taken off site, depending upon what the testing establishes. There are also cases where we bring in clean fill to place over top of our excavated soil that's at the surface in the mounds. This was the case on a site in New York State that we did a couple of years ago, where the state required us to place, I think it was at least 12 inches of clean soil over top of any soil that came out of the hole. So it varies from one site to another.
Thanks.
All right, we have a question from Sarah Gaines. Sarah, go ahead.
Hi, Paul. I just had a very specific question. I noticed on your map that you had a Chicago area, and in fact, it looked like there were a couple of Illinois projects that you had done in the past, and I was just wondering if that's a site, if you recall what kind of site that is and whether we would be able to visit it in person.
Well, we have a number of sites, some done fairly recently and some done a while back. We have, I'm trying to think of the, let me go back to my map here. Yeah, the Northern Illinois sites I would have to look at, but that's certainly a possibility. And it's one of the things where I would just have to get approval from the client and look at and make sure that everything is still there. If it's something we did 20 years ago, it may not still be there. So, but that's certainly a possibility, and we have done that on a number of sites. And in general, I'd say it's 50-50. Some clients say, no, we don't want people coming to visit our site, and others are extremely proud of it, put up signs, and like I say, it can be part of a public park.
Thanks.
That's it for the questions that are in the Q&A box. I want to do a final call. Does anyone else have a question? And you can either just say yes in the chat and I'll take you off of mute, or type it in. Okay, Josh, you might be able to take yourself off mute since there you go. Great.
Sweet. Yeah, so just looking at the map, is there any particular reason that there's not any projects in the Mountain West? Is that just like a market thing, or is there a reason for that?
There are a couple of reasons. The biggest reason is just that there aren't that many industrial sites there, and the ones that are there are generally the types that don't really look hard at our technology. I have come close to doing some small refinery projects in Wyoming and Colorado, but they're generally looking for, a lot of people that approach us see the word phytoremediation and they assume that it means something that's going to be extremely low capital costs to implement, and because of the kind of heavy construction nature of our process, it's not as cheap as some people are hoping it's going to be. So our applications with the petrochemical business, especially with the smaller companies, they're looking for something that's really, really inexpensive. The other reason that there's not a lot in the Mountain West is because of the climate. Some areas, the precipitation is very, very low, and so we're extremely limited in the types of trees that we can use and the amount of water that we can move. But there are, I mean, as I'm sure you guys are aware, you still got a lot of options with regard to trees, and if there's water available, they'll survive. And I mean, one of the good things about our system is that if we can get enough capillary rise in that soil column, and we can put the trees in contact with that, then they don't really care if there's only 5 inches of rain where they are. They've got an unlimited supply of water. So part of it is we haven't done a lot of marketing there either, and so we just don't have the client base. But we are kind of looking at changing that. So, but I'm still thinking that the desert Southwest is, some of that's going to be a stretch to be able to work there, largely because the depth to water, once we get over a depth to water of about 30 feet, it can be difficult to make the system work.
That makes a lot of sense. Thank you.
All right, well, we're almost at our time, so I just wanted to thank Paul for a great presentation and kind of fascinating topic that is relevant to a number of our projects, either currently or further down the road. And as everyone knows, but it's worth repeating, it's the reason we do these talks and sessions is to learn and exchange information and knowledge, but also to introduce ourselves to potential partners on projects. So as we are pursuing work and teaming opportunities, certainly to reach out to Applied Natural Sciences and Paul and Tara, and that information, the contact information, will be on the wiki that is dedicated to this particular presentation on our internal portal, so that you can always find their contact information as well as the presentation and recording. So I'll get all those up there, but Paul, thank you so much for your time today. We really appreciate it and hope we have the opportunity to collaborate with you.
Well, thank you, Allison. I appreciate it.
All right, everyone. Thanks so much. Bye.